So thank you so much for coming. I hope that undefined behavior is something that you encounter every day. So you'll learn a lot how to avoid it or how to actually live with it. Also, yeah, just a small reminder that this is a community event and where we basically all participate. And as long as we are participating, the community exists, right? And I'm super excited also to announce that we have next events planning. As you see, and we discussed before, that we had some bumps on the way with the budget from Google to host. Now it's solved, so we will have a couple more events this year. And if you know Sean Parent, anyone knows Sean Parent? Yeah, he will visit us in October in person, so you'll have a chance to take a photo, whatever, and to listen. Yeah, same reaction actually. Yeah, yeah. So follow us in all our social networks like meetup.com. Thank you so much for coming, Shachar.
Am I? You're okay. Yeah. Hi. Let's see. Excellent. Yeah, so this is a talk I gave at CPP Now, which was May, I think. And it was scheduled there for an hour and a half because the audience in C++ Now like to interject. So what my request for you is, if you have anything to say that is even remotely relevant, just go ahead and say it, right? I'm one of the worst hecklers myself, so I think it's only fair. The talk is about, right, yeah, no, that's, okay. Traditionally, slide number 2 is who am I? And then I spend 5 minutes talking about something that doesn't interest any of you. Some of you already know and some don't care. Sorry. So I'm not going to do that. I'll briefly talk about it at the end if anyone stays that long. What I really want to talk about is who you are, because this talk kind of have two non-overlapping audiences. And those are those that essentially that heard about this undefined behavior, maybe figured it out from the name, and then people told them that, no, that's not what it is. And then there are those who already know about undefined behavior and want to learn more, or my clickbait title that says that sometimes it's legitimate got you here. And what I want to know is which group you belong. So who here do not have the formal definition of C++ what undefined behavior is? Raise your hand. Okay, that's quite a few. And who belongs to the other group? Okay. Who will not raise their hand no matter what I ask? Thank you. So instead of talking about undefined behavior, I'll begin with an example. It's not a very interesting example, except for where I got it from. Where I got it from was a website that a company I worked for paid to have membership, to have a subscription, where you had ideas for interview questions. So somebody thought that this was a good idea for an interview question. Are you ready for a job interview? No, that's not the one we want. Actually, that would be the one I want if it was in the right directory. Never mind. Okay, so square. Apparently I can't spell square. Is this big enough? This, you can't see anything. Is this big enough? Let's take this. Okay, square, here goes. We want a IO stream, and we'll define a macro called square, which will be A times A. Okay, so far, are you with me? Cool. And now I'll define main, and I'll print out. So let's define a variable, then give it the value of 3. And I'll print the square of var. And the question is, what does this program do? I said it's not a very interesting example, but still, someone please answer. Okay, it prints 9. That is a theory. Let's see if we can rule it out. It prints 9. Great. But now let's do one minor change to the program. Let's do this. What does this program do? Prints 20. Can you walk us through the logic? Right. Do you want me to throw this so? Almost. There's a microphone somewhere there.
Okay. So the plus plus var, the first plus plus var will increment to 4 into the second plus plus var will increment it to 5. So 4 into 5.
Okay, so if this expands to plus plus var times plus plus var, that translates to 4 times 5, and that is 20 last time I checked. So the program will print 20. Anyone here thinks that's not, it will do something else? Yeah?
I guess it could also increment it both times first and then continue to evaluate this remaining expression, which then would yield 25.
And the logic for doing that would be?
That it's not specified in which order sub-expressions are evaluated.
Okay, you're kind of off, but not by a lot. I'll expand in a second, okay? But there is one thing you are not wrong about, which is that the program does indeed print 25. No. The brackets inside of the macro are, if you ever get the chance to create macros in this day and age, those brackets are pretty much mandatory, because otherwise, whatever A gets expanded to, if it has operators, will fight with, for operator precedence, will fight with the precedence of the multiplication. So if I don't do the brackets, and I do square of 3 plus 4, you'd expect it to be 3 plus 4, 7, square 49. But if I didn't have the brackets, it will be 3 plus 4 times 3 plus 4. And you'll get 3 plus 4, 12, plus 3 plus 4, and you'd get 19. So those brackets are really, really important if you're doing macros in this day and age, which you really, really shouldn't, especially not these types. Okay, so let's walk through the explanation that at least predicted the right answer. It said, the order of evaluation is unspecified, and therefore the compiler can move all increments to the beginning of the expression. And like I said, this explanation is wrong. However, and this is the important part, the explanation that the website I got this example from is also wrong. So, who here knows what unspecified means? Raise their hand. Okay. Good thing I have a slide on this. So, terminology. First of all, there is something which isn't defined. Something that isn't defined means the standard, okay, C++ is defined by a standard. So there's this document which you can pay a lot of money and buy, or you can go on the website and get the last draft before it was ratified for free. I don't know why you would do that. It's a huge document that is really difficult to read. People who actually read and understood the document are sometimes referred to as language lawyers. And it defines what C++ is. It defines what a compiler should do when presented with a program. But the standard being written by humans, it is possible that you'd feed it a program, but the standard doesn't fully specify how it should be converted into machine language. So that is something which is not defined. And when you tell people you're talking about undefined behavior, that's what they think you're talking about. And it isn't. That's not what undefined behavior is. Except when it is. I'll get back to that. Then there's unspecified behavior. So, well, first of all, there's specified behavior, okay? The standard says what should happen with this program. Then there's unspecified behavior. Unspecified behavior says, the standard says, it is not saying what should happen with this program. I lost all of you, right? Let's try this again. So the standard says, if you do this and this, it is unspecified what will happen. And unspecified means the compiler essentially can pick whatever, right? It doesn't have to document what it picked. It doesn't have to be consistent across cases. It can just pick whatever it is the compiler implementer thought would be best for it at that point in time. And that is not undefined behavior. Then there's implementation defined. Implementation defined, again, is explicitly stated in the standard. And it says the compiler can pick whatever or among several options, but it has to document what it picked, and it has to be consistent. So the first problem with your, what's your name? Christoph. The first problem with Christoph's answer is that the evaluation order of arguments to a function, which an operator invocation is implementation defined. It is not unspecified. It is implementation defined. So the arguments can be evaluated left to right, or they can be evaluated right to left. The compiler implementer is free to choose whichever of those works best for them, but they have to document it, and they have to be consistent. Which means that if we go back to, if we go back to the square example, and we return it to the way it was supposed to look, so that gets expanded to plus var times plus var. And the evaluation order between the two plus plus vars is implementation defined, and that still doesn't explain why 25, because it means that we may not get 4 times 5, we may get 5 times 4, but that's still 20. So, and that's, by the way, the explanation that the website gave for why 25, without explaining why that makes it 25. And like I said, my company paid money to get access to that. So, what's going on here? What's going on here? Yeah.
So we modify the same variable times between sequence points. I'm not sure if that's correct for C++.
I'm getting to that in a second, okay? So what's happening here is called undefined behavior, which is behavior upon use of a non-portable or erroneous program construct of the erroneous data for which this international standard imposes no requirements. So, right, all clear, I'm done here, we can go, right? No? Yeah, you have to say something, otherwise nobody will say anything. Okay. Let me put it in more human readable words. Undefined behavior, explicitly stated in the standard as such, means the compiler is free to assume never happens. Now, that seems like a very strange thing to say, and we'll get to that in a second, but yes, modifying the same variable without a sequence point is undefined behavior. So, what is a sequence point? A sequence point is something where the standard guarantees that A will happen before B. And because the order of evaluation of a function parameters is implementation defined, the order of evaluation is called unsequenced. And yet they both change the same variable, and that's defined in the standard as undefined. So it's not defined in the standard. It is defined. It is explicitly referenced in the standard as undefined behavior. So when the compiler says 25, it's not doing what we expected, I think, right? I mean, except from Christoph, nobody here expected that program to print 25. But it is compliant to the standard. Which brings us okay, that, like I said, it's not a very interesting example. So let me give you an interesting example. I call this example Chekhov's gun, which is a bit misleading because it's not my example, and B, that's not the example's official name. Problem is, I do not remember where I saw it. It's a great example. I don't want to not use it just because I can't give it credit, and I think the name fits. So here goes. Where are we? Okay. So, probably want to click the right window. Just a fun. So, as before, we want output. First thing we do, we want to define a pointer to a function. Everybody here, of course, know how to define that, right? What you do is you write the function this points to. So let's do a function that returns int. We'll call it a gun and doesn't accept any argument. And then, in order to turn it into a pointer to a function, we just get a pointer to it, which we do by doing this. But of course, that means return an pointer to an int because of precedence. So we need to fix the precedence with brackets. Okay, and that's a variable called gun, which is a pointer to a function that accepts no arguments and returns int. And one last thing, I'm going to do it static. Because of reasons. Next, I want to define a function with this signature. Let's do it something interesting. Let's erase the hard disk. Now, since I am not quite crazy enough to do that, let's just say we erase the hard disk. So, last, let's do a function that matches the two, like they're so good to each other, right? They have the same signature. So let's do a function called loadGun that says gun equals bullet. This function is not static. Now, actually calling loadGun and calling gun would be crazy, so I'll do just one of those. I won't call loadGun because that would be crazy. I'll just call gun. Are you with me? What will this program do? Right. Your hand seems to be up for some reason.
I think the kind of takeaway is that calling gun was uninitialized as undefined behavior. So the compiler can assume it never happens, which means the minus branches.
I'm asking what will the program do? So, the answer is, and I'm quite surprised nobody thought of it, it will segfault, right? We're literally calling an uninitialized pointer. Why would one think it would do anything else? Right, good point. It is initialized because global and static variables that are not explicitly initialized are initialized to 0 bits, which are a null pointer. So it is initialized to null. Good point. Let's do a slight modification to the command line, though. And as people have pointed out, dereferencing a null pointer is undefined behavior. And so the compiler is completely within its right to do this. But why? Right? I mean, just a second. Forget why it did this. Why would we want to allow that in the language? Yes. I am nothing if not accommodating. Happy? The strangest things make you happy. Yeah. I don't want to know any more information. Do go on. OT? O3 on GCC? Okay, so the first question I want to tackle is why would we want in the language something where the standard says anything can happen? I mean, the very fact that we turned on optimization and the program did something different is bad enough. Why would we want that? Why we would want to invite that into the language? And the answer is we must. And to prove it to you, let's define our own language. Okay? I'm going to leave the definition up to you guys. I wanted a couple of restraints though, okay? First of all, I want it as a high performance language. So I don't want every memory access to be checked at runtime. Okay, so, and essentially I want it like a C-like language. So I want pointers, I want them to be nullable, and I want memory accesses not to be constantly checked. But otherwise, you tell me what you think should happen. For example, when we dereference a pointer that happens to be null, what should the standard say should happen at that point? Panic. Panic is in the OS crashes. The entire OS. That's a bit technically challenging because let's settle for a sec fault. No, because it's a strange. Think about it. What you're saying is that the standard says that a program dereferencing a null pointer has to panic or has to segfault. Fine. Null pointer dereference crashes the program. That's what we defined should happen. What about this program? What it does, for those who are not Unix savvy enough to read it, first thing it does when the program begins is it catches the segmentation fault signal and it directs it to a crash preventer which says clean exit. And now, because our language mandates that null pointer dereference crashes, the compiler is obligated to not allow this to compile. Does that make sense to anyone? So what can we do?
We have to do a check at runtime, whether it's nighttime.
I said I do not want that. I want the program, the programming language to be performance oriented. I do not want every memory access to be checked.
You can't get it, at least if you are, for example,
Well, let me offer you a solution.
embedded systems and you don't have an MMU that makes you a garbage.
But let's take a step before that, right? Let's say, okay, we do not crash, but the signal is emitted, right? So we're saying null pointer dereference emits a segmentation fault signal, and then if you catch it, that's fine. But then, like he said, there are embedded systems where null pointer dereference 0 is a legitimate address in memory. You can access it. There were cases. This, as written, will not run properly on Linux, but there was a case in the Linux kernel when an attacker managed to effectively create this effect which maps page 0 and then create null pointer dereference that the compiler optimized out because it thought it was undefined behavior and cause a security fault, security bug in the Linux kernel. So, okay, what can we do otherwise? The thing is, but how would you know there is an error without monitoring the... The thing is, UBs are a necessary evil for any programming language that is even remotely the way C or C++ are built. There is simply no way you can define all behaviors, and you could leave this unstated, but here's the thing I left out before. The C++ standard defines behavior that is not defined as undefined. Oh my God, that was a horrible sentence, right? I mean, anyone need me to repeat it? Please say no. Okay. Behavior that is not defined, so behavior that the C++ standard doesn't explicitly state what should happen, is defined by the C++ standard as undefined behavior. And if you think about it, there is no other way it can treat it, right? There's nothing else it could say about it, because it doesn't say what should happen, so anything can happen. I will make one observation, though. It's an observation, it's not a hard and fast rule. In fact, for square, it didn't happen. But I think everyone are okay with Chekhov's gun crashing, right? I think everyone understands that, yeah, we dereferenced a null pointer. Of course, we don't expect the program to just continue executing. Where people start to say, whoa, 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 what's going on here? How am I supposed to debug this? Is when Chekhov's gun actually fired the bullet, right? That's the point where people, and that happened when we introduced the optimizer, right? Without optimization, it didn't. When we optimized with CLang, it did. Which means that the bad behavior is a result of optimization. Again, not a rule, just an observation. Which means I want to now put a pin in the undefined behavior talk, put it to the side, and instead let's talk about compiler optimizations. Let's talk about what are compiler optimizations. What does the compiler do when we say O2? And to do that, I'm going to use a program, a very, very sophisticated program, which will not show up because I have a privacy policy, which says, do you want to increase the font size? Okay. So we define a function, we define a variable in that function, we assign a value to it, and we return the variable. And the thing is, that compiles into quite a bit of code. But if we turn on optimization, then what we get is return 42. And the question is, how do we get to this from this? Okay, what does the optimizer do in order to do this piece of magic? So that requires me doing three things, more or less. The first is understand what this is, where that came from. And that requires explaining something about intermediate representation. Most compilers, not all of them, but most modern compilers, do not compile that directly into machine language. Instead, they compile that into some intermediate form. And I'm going to use something which is based on, but not identical to an intermediate a standard intermediate representation called LLVMIR. LLVMIR can be viewed by me doing emit LLVM, if I'm correctly. Right, so it looks something like this, but I'm not using this specifically because I need something cleaner. So we are going to use, no, why did I do that? So this is more or less how that looks. Again, this is not LLVMIR per se, but it's close enough. So what do we have here? We have the definition of the function. And then the first thing we do is create a function frame. Does anyone here not know what a function frame is? Okay, there are a few. So whenever we have a function that defines local variables, these variables need to be stored somewhere. And that somewhere is the stack. And we have a stack pointer. I assume everyone here knows what a stack pointer here is, right? Okay. So we have the stack pointer, and we could just, the stack usually on most platforms grows down. So we could subtract value from it, which effectively allocates space, and then use pointers that are relative to the stack pointer in order to access those memory. But the stack pointer tends to move about a bit. So instead what we do is we copy the stack pointer to another register, which most platforms called a frame pointer. So of course, Intel had to call it a base pointer. And then we do the subtraction. And now the frame pointer sits dead in the middle. Below it are our local variables, and above it are the function parameters. And it's constant throughout the function. Of course, it needs to be saved, so the sequence is push the frame pointer to the stack, move the stack pointer to the frame pointer, and then subtract value from the stack pointer. And then the exit from the function is move the frame pointer to the stack pointer, pop the frame pointer, return from the function, no matter what happened in the middle. So that's the function frame. It's a standard way of doing it. And functions that allocate variables on the stack pretty much have to do that. I won't go into the details too much. I will point out that you will notice that that's exactly what happens here, right? Push RBP, that pushes the base pointer to the stack. Move RSP to RBP, because Intel, of course, the destination is on the left. And then subtract 4. And that's actually you don't need to subtract because there's only one, never mind. But, and then you use that value, RBP minus 4, as the address in which you store the variables. So that's literally what we see. And then the return, pop RBP. And because we didn't change the RSP, we don't need to change it again, and return. So all of that is encapsulated under the line create frame. The next thing we need to do is allocate space for this new variable. And we're doing this with an allocation function that says allocate on the stack. And we figure out this is an intermediate form, so that's enough for us at this point. And later on, we'll figure out exactly what that means during the code generation. And what we get back is a variable I called %1. And what we're doing here is called SSA, single statement assignment. Each one of those % number gets assigned exactly once throughout the function. And for optimizations, that's very helpful to figure out the program flow. We'll see why in a bit. So %1 for now and until the end of the function is the address of our variable. At this point, we need a literal. So we have %2 being 42, the literal number integer 42. And now we're saying store %2 into the pointer that %1 point to. And that's our allocation, right? Allocate a variable, initialize it. And now we move to the next line. And the next line says return variable. So now we need to load this variable. So we load the value from %1 and we assign it to SSA3 and we return SSA3. So that's our function. And of course, I lost the... Where is it? Ha, you're not supposed to see that. Okay, so now we need to set optimization rules. Define optimization rules that will turn that into something better. Ideally, optimization rules should have a few guidelines, follow a few guidelines. The first is that we want as few preconditions as possible. So we could define an optimization rule that says, if you see an allocation and then an initialization and then a load, then turn that and a load and then a return, then turn that into just returning the value. And it will optimize this function, but it will not optimize any other function. Right? So we want as few preconditions as we can, because that will mean the optimization rule can be applied more widely. And the other is kind of obvious. An optimization rule is a transformation of their code. It needs to maintain semantics. So the program before and after needs to be the same program. I think that is kind of obvious. However, the semantic we need to maintain is the observable semantic. So we don't actually need to do the same program because by definition, then we can't optimize. We just need the program to behave the same way under all conditions. Is that clear? Yeah. That's, by the way, explicitly stated in the C++ standard. And ideally, the effects should be localized. It's not strictly something we want, but we can't get the other two without this also being true. So, what can we optimize here?
We have a load instruction, and we see another store instruction before, and the pointer must alias, and there's no other store in between that may alias. Then we can say, okay, we take directly the value from.
Right. Okay. So, if we have a load, and we see the store, and a bunch of other conditions that says that we are allowed to use that. I'm sorry for kind of. Then instead of doing the load, we can just directly take the value that was stored, right? We see a store. We see a store to %1 here, and we see a load from %1 here. So instead of using %3, we can take %2 that was used here. Does everybody see that? And now we can eliminate this line and instead just use %2 everywhere we would otherwise, we currently use %3. So the program looks like this. And when we've just made it simpler. Okay, what now? Let's see if anyone else wishes to take a crack at it. Okay, Christoph.
Yeah.
Okay.
So I guess next we want to eliminate the dead store. And for that we have to know that nobody is ever going to read this value again.
Right. So what we have here is a store into a location that goes out of frame. Right? At the end of the function, this location becomes invalid. So, and nobody is going to read that location. So we can eliminate the store. It doesn't matter. Now, notice something. When I said nobody is reading that location, that didn't used to be true. It's true now, but it wasn't before. So when we're saying nobody is reading that location, we're talking about the program after we've already started massaging it to be more optimized. We don't care how it was before. If that transformation maintains semantics, and now nobody is reading it, then that maintains semantics. So we can eliminate this line altogether. We're using undefined behavior all the time. Okay, what next? Yeah. Someone pass her the microphone.
You can drop.
Yeah, throwing that microphone is funnier. I will grant you that.
We do not need this %1.
Closer, I'm sorry.
We do not need this %1. I mean, we can give back 42. I mean,
I'm sorry, I didn't hear.
I think, I mean, this %1 is not used, so we just can go and return 42.
Right. So we have SSA1. We allocate memory in order to keep it in that pointer, and we're never using it. And that's the power of single statement assignment. If we had multiple assignments, then the logic of saying we're never using it would be much more complicated. But because we're only assigning once, if we don't see it anymore, we're not using it. And if we're not using it, just cut it out. Okay, what next? Yeah?
I think it's single static assignment.
I will not go in, maybe. Okay.
We want to make constant propagation and return 42 immediately.
That is returning 42 immediately. No, the next thing is the create frame. We're creating a frame in order to store local variables. But we have no local variables. We just eliminated the last one. Well, the first one too, but never mind. So we don't need the frame. And this is a function that simply returns 42. Now, what you'll notice are two things. First of all, each one of our optimization steps was self-contained. It made sense outside of this particular function. You can think easily think of other cases where it would make your program simpler. And it got us from A to B. It got us from the original program we saw to return 42, which was obviously what this program should be. And this, look at very strict cases, very small context, do optimization, just do them repeatedly, is called peephole optimization. The other thing about those steps we took is that each and every one of them relied on undefined behavior. That may sound a bit surprising, but let's go back to the first one. It relied on the program not invoking undefined behavior. Okay? So let's look at the first one. The first one said, if we have a store, we see the store and we see the load, then we can just pick the value from the store location. We don't need the load. And that is true if there is no other thread that has a pointer to that variable. Or if we don't call a function that, so we can do that even if there's a function in the middle, because this variable is a local variable, and if we have not passed a pointer to that function, we can assume that function did not change that variable. But it could have calculated the location and done it anyway, right? Except we all understand that if a program that does that, yeah, whatever, right? We all understand that intuitively. But that's exactly what undefined behavior is do that, you're on your own. That is precisely what undefined behavior is. And when we optimize this away, we assume nobody will be reading the variable. When we optimized this away, we assumed nobody relies on that stack area being used. And when we use this away, we assume nobody will want a backtrace. Because when you're doing a backtrace, what effectively happens is the fact that there's a frame pointer allows jumping between the contexts. And a function that optimizes away the frame pointer will not appear in your backtrace, as well as a function getting inlined and other stuff. So
Getting a backtrace isn't undefined behavior, right? Or would you say it is?
what I'm saying is it is not defined that every function you call will appear in the backtrace. So let's look at Chekhov's gun. What happened there? What happened here is called devirtualization. So what is this? Presumably, calling a function through an indirect call is slower than just calling the function outright. I'm saying presumably because I actually gave a talk that tried to claim otherwise, and when I tried to benchmark it, it started as a tongue-in-cheek, just to tell people, don't optimize before you see there's a problem. But as I started writing benchmark, it became completely unclear that that is actually true. Like, completely unclear. But presumably, calling a function through a pointer in direction is slower than directly calling the function. And therefore, whenever we call a virtual function, the compiler says, whoa, whoa, whoa. Yeah, whatever function I'm going to call depends on what happened in runtime, but maybe I can predict. Maybe I can reason about what is going to happen in runtime, and if I end up with just one option, then I can call that option directly. I don't need to actually go through the indirection pointer. So, first we begin with the pointer. The pointer here at line 3 is static, which means the compiler, first of all, says, I can reason about what the value this can have. Because if it was not static, if it was just a global, the compiler doesn't know that maybe another translation unit changes it. And then all optimizations are out. But this is static. The compiler says, I know who is going to access it. What happens if someone accesses it despite it being static? Undefined behavior, right? The compiler need not care about that case. And then it says, what are my options? Option 1 is what actually happened. So gun is going to be null. And option 2 is that another translation unit called load gun. Because load gun is not static. So that is possible. So I have 2 options, and therefore I cannot devirtualize the function. Except one of those options will result in null pointer dereference, right? So the options are someone called load gun, and therefore gun points at bullet, and bullet is going to get called. And the other option we don't care about because it's undefined behavior. And if we don't care about it, then we don't need to consider. Anything we do when gun is null would be considered okay, is within the spec. So we just assume that doesn't happen. And now we're left with one option. So great, we can devirtualize the call and call bullet. Now devirtualizing is important, not because virtual functions are slower than concrete functions, but because if we know what function we're calling, we can inline it. And while inlining is not something that makes your code faster, it allows us more aggressive optimizations, and those do make your code faster. So devirtualization is a thing we want the compiler to do. And voila, all your bits belong to us. And one of my takeaways is that null pointer dereference doesn't always look like null pointer dereference. Let me give you a couple of real-time life examples. And when I say real life, I mean an engineer came to me and says, what the hell is going on here? I don't understand what is, the first one is taken from a chip we were developing, which means that this code did not run on a computer, it ran in an RTL simulator. So there's this code that simulates each and every logic gate in the whole CPU. And now the engineer is looking at graphs of what changes over time, and he was expecting a PLL to be initialized. PLL is a unit that generates clock by doing some math. Or more precisely, you need to do some math in order to initialize the PLL. And he was getting completely wrong results. Now, since the code was running on a CPU being simulated, the first question is, maybe it's a bug in the CPU. You had a question? So he opens the code, he doesn't understand what's going on, he comes to me. And I open the code, and I don't understand what's going on. Does anyone here see the problem? Nope. Param 2 was 1. But the thing is, Param 2 was run at compile time. So the compiler started generating code for compile time execution, and counted the division by 0, said, whatever I have right now, that's what I'm returning. And that's it. Yes.
Because I wanted to say it would optimize the loop completely away because you cannot get into the loop because it would be...
I have no idea what exactly it did. I will tell you what it didn't do. It did not issue a compilation error. Example number 2. That one's a beauty. So we have a code that is supposed to read from a GPIO. So we have memory mapped registers, and we start accessing it. And the engineer comes to me and says, here's the thing. The assert on line 6 triggers. And when I ask what the value of GPIO is, it tells me 5. So I said, well, I know the value is okay, so I removed the assert on line 6. And then, anyone? The assert on line 5 triggered. So I removed the assert on line 5, and then crash. Anyone else wanna? The compiler issued the symbol GPIO set, but issued no code.
The MIO other is not initialized because you're taking the address with it, like,
No, but it's as good a guess as any. Calc data address dereferences the second argument. And what happened here is that line 6 was the last chance this program had of not triggering undefined behavior, which meant that the compiler now has 2 options. Either GPIO is more than 32, so 32 or higher, in which case we assert, or undefined behavior, so we don't care about that case. So we just assert. And now we removed that line, so it had the same reasoning on line 5. And now we removed that line, and it said, well, if you call this function, you're something that begins with an F. So whatever. I'll give you the symbol, so you can call it, but whatever happens to get the same address is what you'll get.
Would you have had an easier debugging experience if you didn't compile with optimizations in this case?
Not all code can be compiled without optimization. This particular code is part of, was supposed to go into the ROM of the chip. It had a certain amount of allocation, and running this code was done in RTL simulation. Okay, RTL simulation, it depends on the size of your design, but in that particular case, I think it was something like 2 hours per millisecond. So every millisecond of execution time took 2 hours of simulation time. So you kind of want to be conservative about the amount of time you say, okay, let's try. And now unoptimized code runs slower. So no, that was not a viable option in that particular case. Now, the thing about this flow is that I'm hard-pressed to say where it stopped making sense. I mean, it's obvious that the end result doesn't make sense. Okay, it does not make sense to issue a symbol and then not put anything there. But at what point did it stop making sense? I mean, we put asserts. And the thing is, undefined behavior has its advantages as well. Okay, consider this program. What we're doing is we're looping until sum gets above a certain value. And then depending on whether param is below or above a certain value, we increment sum by a different function. Now, as a programmer, it should be fairly easy to reason that since func1 and func2 don't return a value that is too big, What's going to happen here is that we'll at first run the first function for the first 10 iterations, and then the rest of the iterations until some get to 5,000, we'll run the second function. And now, as an optimizer, we can optimize away the if by splitting it into two loops. One for the first case and one for the second case. But we can only do that if we know param doesn't loop around back to being low. Now, as a programmer, you look at that and you say, well, come on. But the compiler is not allowed to assume that except if param is a signed integer, in which case it is allowed to assume that. And I know people who work in high-performance computing and in writing GPU codes really, really love this optimization. They really, really love that signed integers cannot overflow because it generates more efficient code. And like I said, in the Chekhov's gun example, if we had a second file, that's what it did. So what it did is we have a static variable with a constructor that calls load gun. So that runs before main. And if we just compile this second file in with the Chekhov's gun example as is, then the optimization suddenly makes sense, right? We did optimize away a virtual function call and did the right thing. The semantic was correct. And that's the problem with undefined behaviors. Each one of them seems to make sense to a degree, except the end result seems completely illogical. Thing is, the standard kind of is dealing with that. Let me show you 3 standard library calls, and raise your hand if you know them, right? The first is bitcast. How many people know bitcast? More than I expected, right? So that's like 5% of the people here. The second is start lifetime as. Again, raise your hand. I've got 1. 2? You too? No? Don't be panic. I'm not going to quiz you on what it does. Ooh, so what? No. And the third is lounder. Oh, so what does it do?
I don't know. I don't know what the function called. I copy-pasted some example from some C++ guru that said this particular use case was okay.
Bitcast takes a value and uses the same bits to give it a different static type. A start lifetime as, they're getting from concrete to fuzzy here, which doesn't apply to what they do. It applies to my understanding of what they do. Start lifetime is, the standard has a lot of places where it talks about a variable lifetime. And C++ prides itself that the lifetime of variables is well defined. Problem is, when class has a constructor and a destructor, it's very clear what the lifetime is. When it's plain old data, less so. And that's a problem because you're not allowed to accessing a variable before it begins its lifetime is undefined behavior for reasons that are kind of obvious, right? But when does the lifetime begin? So this, you're supposed to call this in order to say now. I should point out that the person who submitted the technical report asking to introduce this said, and I loosely quote from memory, I have not come across a single case where that turned out to be a problem. And about Launder, the quote is, there are about 5 people in the world who knows what that does, and nobody else needs to. It's a barrier of some sort. If you know what a barrier is, fine. You did not understand it better than I did, but you did not understand it any worse than I did. If you don't know what a barrier is, learn what a barrier is. It's very important, but not this one. And the thing is, those 3 are, by and large, a reinterpret cast. Okay? That's what they are. Now you'd say, okay, fine, but reinterpret cast is a very dangerous operation, and it can introduce undefined behavior, so it's good that we eliminated those, right? Wrong, because I can't find it right now, but somewhere here is the text that says that if the source and destination types of a bit cast do not match correctly, then that's undefined behavior. So essentially, where reinterpret cast would logically be an undefined behavior, bit cast would also be undefined behavior for precisely the same reasons. And the thing is, null pointer dereference. Who thinks dereferencing a null pointer is a good idea? Come on, raise your hand. Right? Except we used to check, you know, if you have a struct and you want to know what the offset of a variable of a member is into the struct. Okay? So you have a struct and you want a specific member of that struct because, for example, you're going to get a pointer to the member and you want to calculate back the struct position, right? So you need the offset. Now today we have offset off, which is a keyword. But before we used to do this, right? So we had a null pointer. We reinterpreted cast to be a pointer to the struct in question. We took the member M and we took its address. Now, since null pointer is 0, the address is the offset. So, and then we took the pointer and we static cast it to a size t. That's how we used to do it. Except this is considered a dereference, and this is a null pointer. So by definition, this macro is a null pointer dereference. Now, of course, I think we all understand that it's not actually referencing the memory, right? All the arithmetic happens without actually accessing any memory. But if dereferencing a null pointer is undefined behavior, then the compiler may assume that this doesn't do what we think it does and optimize it away. And at this point you say, side note, if you have a virtual base class, then this does in fact access the memory. Does anybody here know what a virtual base class is? About the same amount as heard of bitcast, which is sad, but never mind. Yes, it is sad. You can watch a talk given in CPPCon 2023 called Optimizing Aware Virtual Functions May Be Pointless, given by me. For more details. Forget my own name next. But assuming no virtual, and by the way, if you try the macro offset off on a virtual base or something with a virtual base class, then it won't compile. I'm not saying there's no use for having a keyword. What I am saying is that keywords can't cover everything. Because, and this is true, there are other use cases that the keyword doesn't cover. For example, there is a technique called intrusive pointers. And in particular, this particular case, it's intrusive linked list. So I'll give you the example with a reference counted a smart pointer because it's easier to understand. When you use a reference counting, then you need two memory areas, one for the actual value and one for the reference count. And that's annoying, and it hurts performance, and it hurts versatility. However, maybe you know when you define the type, you know you will want to use it as a smart pointer with reference counting. So you can define the reference counter as part of the struct. That's called intrusive reference counting. And it is the most efficient way to do reference counting. And it has the wonderful property where you can get a naked pointer to a type and convert it to a smart pointer. So you can increase ownership from a naked pointer, which gives you more versatility with standard libraries, and in generally is a very interesting quality. So it's very useful. However, a variant of it is intrusive linked list. So again, a linked list needs pointers to the list, other list members. And if you know a type is going to participate in a linked list, then there's no reason to allocate it separately. Just include it in your type. But then, what you're pointing to is not the whole type, because then you'd have circular type system. What you're pointing to is the member of the type where the node is. Which means you now have to convert this back to the actual type, which requires offset off. Thing is, if you want to templatize it, then you can't. Because what I'd really like is for the template parameter to be a pointer to member. Anybody here know? Who knows what a pointer to member is? No more than those who know what a bitcast is. That's like, pointer to member is never mind. But do look it up. It's an interesting construct. It does the same thing as what I just said. So it essentially is an offset off, except it's within the type system, so it's type safe. Do not use offset off before you know what a pointer to member is. But this requires that we convert a pointer to member into an offset, and we can't do that with offset off. So I really want to use the macro I defined before, except I can't because it's undefined behavior, because I'm dereferencing a null pointer. But at least we know what are the UBs, right? The standard lists them, right? I mean, I just said they're explicitly defined by the standard. I said it. You heard me say it. Except there's no comprehensive list. So go to Wikipedia, C++ undefined behavior, and you will have something along the lines of C++ undefined behavior are things that a compiler can assume never happened, yada, yada, yada. And there are things like null pointer dereference and signed integer overflow. So there's a list there, but it is explicitly stated that it's not comprehensive. Okay. But maybe we can go over the standard and pick those up. Except, like I said, anything not defined by the standard is undefined behavior. Fine, so not those. Except, sometimes you invoke undefined behavior and it does do what you expect, right? So take the offset off example, right? Maybe you don't really have a good option otherwise. Fine, but at least we can search the standard and undefined behavior, there. That's from the, I think it is the C++ 23 version of the standard. Again, not the C++ 23, the last draft before it was ratified. Right? Kinda. Because sometimes it says the behavior of the program is undefined, and it does mean the same thing. Also, if you just search for undefined, you'd get false positives, because here, that's not an undefined behavior. And sometimes the word undefined doesn't, well, behavior is undefined will find 74 matches. But occasionally, the standard will confuse. Because look what it says here. Then the behavior is either unspecified or undefined. That, ladies and gentlemen, is a bug in the standard. The behavior in the standard cannot be either unspecified or undefined. If it's unspecified or undefined, it's undefined. Who's talking? Okay, yeah.
Isn't this the second concept that we have to say that every implementation may decide on exactly one behavior
No,
for
because
this, but it must be consistent with that?
No, that's implementation defined. Unspecified means that you can do here one thing and the next. And the thing is, the word undefined may not appear at all. Okay? Now, technically, ill-formed is not the same as undefined, because undefined is runtime and ill-formed is compile time. I don't think as a programmer we care. I should point out that there are cases where the standard says, if this and this happens, the program is ill-formed, no diagnostic required. Now, to be fair, the cases where the standard says this are usually cases where diagnostic is impossible, because the combination of events that cause this to be ill-formed are across multiple files, which has the desirable side effect where the optimizer will not step in and completely transform the symptoms to the point where we can't connect them back to the root cause, unless link time optimization is enabled. So, yeah. How can things be made better? So, first of all, that's not on you, right? That's on the language and compiler designers. I would love to see UBs that have served their purpose removed. For example, the reason a parameter evaluation order is implementation defined, anyone ever wonder about that? Have you found something? Let me give you a solution. I'm old enough, I know my hair is still black, but I am old enough to remember. Back in the days, say early PC, so 16-bit PC DOS, registers were few and specifically named. So there was a register called stack pointer, and that's what it did. And you could push and you can pull and not a lot else. And there were not a lot of them. So the 8086 had like 5 registers. So when you wanted to pass parameters, arguments to a function, you did that on the stack. So you would evaluate, push, evaluate, push, evaluate, push. And Pascal indeed defined the push order, so the binary, to be from left to right. So left to right, okay? The order you read the code. And then C came along, and C wanted one specific function called printf. The thing about printf is that in order to know how many arguments printf got, you need to look at the first argument. Which means that if you push the arguments left to right, the top of the stack contains the last argument, and you have no idea where to look for the first argument because you don't know how many arguments there are. And therefore, C changed the ABI to say that arguments are pushed to the stack right to left. But now, because we don't have a lot of registers to store values we've evaluated but not yet pushed, it only made sense to also evaluate arguments right to left. So that's why we don't evaluate arguments in the same order as we read them, because ancient platforms couldn't handle that. And then they relaxed it to say implementation defined. Fine. I mean, at this point, we understand that the interaction between implementation defined and sequencing would mean we would rather have it right to left than implementation defined. But who knows, maybe there is an implementation would prefer left to right. So yeah, I would love to see that one removed, for example. I don't think it serves a good purpose anymore. The thing is, and I said before, UBs are a necessary evil. My point here is that UBs are a necessary evil. Couple of other things. Compilers, if you detect undefined behavior and it caused you to erase the whole function, say something, right? And not all compilers are equal on that front. And by that, let me show you the square example again, which was a while ago. And I'll make one small change to the command line, okay? It's one of those changes that are position dependent. Where was it? Oh, yeah, okay. Okay? It can be done. The technology exists. The error message is not great. Multiple unsequenced modification to var. How many of you would understand what that means out of this, the context of this talk? But at least it said something. Not only it said something, when I run it, it returns 20. The technology exists. And there is something called the UB sanitizer. GCC has it, CLang has it, Visual Studio has it in their work plan sometimes. I actually talked to a Visual Studio developer and he said, well, we have more urgent things right now, but we do plan to get to it eventually. And what it does is it makes those implicit assumptions that the optimizer does explicit and checked at runtime. And so if you're triggering an undefined behavior, the program crashes. Of course, that's for sanitizing, that's not for production code. If you want to reach me, I have LinkedIn, I have Twitter, I have Mastodon, I have a YouTube channel, and I welcome your input and well wishes and whatever. Thank you very much. And with 25 seconds to spare.
Maybe I'll quickly add, I looked it up. Unspecified is actually defined in the standard. It's implementation defined, minus the compiler manufacturer doesn't have to document it. But unspecified is well defined instead of UB, which is ill-defined.
It is well defined, but it doesn't have to be documented and it does not have to be consistent.
But I think it's a good thing if you're at least able to be unspecified or undefined, because it means one of them is not an
No, it is not
program.
a good thing, because as someone who writes the program, I don't know which one the compiler picked. So I have to assume undefined.
Maybe. So I look at it that way. Look, this at least adds some programs that are not ill-formed, right? And so for these programs, the compiler cannot YOLO you and do whatever it wants, right? So it will do something slightly less crazy.
But the compiler can do that for things that the standard defines as undefined too, right? The compiler can pick something that the standard says is undefined and say, I'll do it consistently in this way, and that's conforming to the standard because the standard says you can do anything, and anything can also include this specific way. So it doesn't change anything.
And we can take this offline later. We can take
No
this
problem.
offline if you want, but
No problem. Come at me. I've worn you down.